Okay, so let's talk about our surface analysis overview plus EDS 101. That's what we want to do. We want to cover today. I don't know how much time we have, but we should have enough material for 1 hour. Okay. So, definition of surface. A surface is the outermost layer of any physical object. And it is extremely important and responsible for interfacial characteristics such as chemical reactivity, adhesion, wetness, and electrical properties of the material. When we are in the material science research world, this is true. But what is the outermost layer? The answer would be different depending on whom are you talking to. Okay, so this one is self-assembled monolayer on the substrate. Okay, it is in a fraction of nanometer world roughness on the surface, or our typical surface in the characterization, nano-characterization facilities, everyday world, microstructures, nanostructures of the surface, something like that. But the surface can be referred to the surface cracks on the concrete slab, something like this, or our planet Earth has surface water or land surface. So we all talking about quotation mark surface, but the dimension, thickness of the surface we are interested in would be very different depending on the definition or what kind of interest does the person you are talk to has. Okay. So let's compare various surface analysis techniques. I included EDS or EDX here because in a relative sense, it can be used as a surface analysis tool. Okay. But first left 3-1, OJ, electron spectroscopy, low energy ion scattering spectroscopy, X-ray photoelectron spectroscopy. Those 3 instruments are generally considered to be a surface sensitive tools in the material science world. EDS typically not. Okay. So let's start with the instrument we don't have, OJ. It's often called AES. And for when you think about characterization tools, what's in and what's out, those are important things. You have to pay attention to those things. So for OJ, AES, input is electron beam. Typically a few kBs up to 10 kBs, that's the impression I had. I have never used OJ AES in person, so I'm not too familiar with this technique. So electron beam in, primary electron beam in, and output, what we want to detect is OJ electron. Elemental range is pretty good, lithium to heavier elements. The lateral resolution, depth resolution, maybe, lateral. No, this must be the XY resolution, can be as small as 20 nanometers. Okay, that's pretty small. And detected depth, sampling depth would be, say, 3 nanometer-ish. Something similar to XPS. Okay. The detection limit, I got number from somewhere, 1% maybe, and quantitative maybe, accuracy 30% maybe. Depth profiling by using the spatter gun is possible and pretty standard for OJ. The biggest disadvantage of this technique, in my opinion, I asked XPS application specialist as well, is it cannot deal with insulator analysis. Chemical state information, binding state information, maybe, but there is a limitation. So insulator, it works great for conductors, but not so much. And the surface damage. So yes, we can focus electron beam into very small probe size, like 20 nanometers, but the damage to the surface is significant. So that's main reason why we cannot deal. This technique cannot do well with insulators or poor conductors.
Is there an OJ electron spectroscopy tool nearby in Colorado somewhere, Tomoko?
I think Steve George's lab may have this attachment to their XPS.
Right.
But the OJ is not very popular technique because of the limitation, the analyze. So up to that analyze insulator, no, all the spec looks pretty good. So we can go to very small spot size, yes, surface sensitive, maybe some chemical information, but it doesn't work too well for insulators or poor conductors. So therefore, not too many AES standalone instruments around the world. That's how I feel it. Okay. And next to something we have in 361, so QTAC 100 from IonTOF technique is low energy ion scattering spectroscopy. It's called LEIS. Sometimes it's called ISS, but IonTOF people does not like to be called as ISS. I will explain the reason why later. What's coming in is noble ion. What we detect is the same ions. Okay. Elemental range, about the same, lithium and up. But in practice, LEIS is not very good at detecting lighter elements. So you wanna, oxygen, we can detect all the time. Carbon is kind of the lowest. Yes, but sometimes not easy to detect carbon clearly. The XY resolution, 10 micrometers. That's the smallest spot possible. About the same as XPS. We wanna, yes, but it has a limitation because we cannot focus, in this instrumentation, we cannot focus ion beam too small. On purpose though, okay. The sensitivity, surface sensitivity is surface monolayer. That's the strongest point of LEIS. And pretty much, I don't think other tools can do it properly. If you are talking about surface monolayer, detection limit, it depends. Quantitative, maybe yes, but since it's relatively new technique, finding the good standard reference material is always a challenge for this technique. Accuracy, because it strongly depends on the reference material. Accuracy is kind of question mark, I left it. Depth profiling, it's possible with the argon sputter gun, but maybe down to not so deep like microns, maybe like 10, 20 nanometers, because if you go deep, you lose the strength of monolayer information thing. Analyzing insulator, yes, it's possible. The charge neutralizer is equipped. Chemical state information, no. I will explain little later. Okay, XPS. In my opinion, XPS is the most popular surface analysis instruments around the world. X-ray photoelectron spectroscopy. Its old name is ESCA, electron spectroscopy for chemical analysis. That's why the software of the Kratos Supra's UI is called ESCAPE. Okay. What's coming in is X-ray, monochromated aluminum of silver X-ray. And what to be detected is photoelectrons. Elemental range, lithium to heavier elements. And even though the sensitivity factor of the lithium is pretty low, but lithium can be detected nicely. Carbon, yes. So anything higher, it's great. The spot size, smallest spot size is about 10 micrometers, about the same as LEIS. Sampling depth is about a few nanometers up to 10, depending on the material system. Detection limit, maybe 1%, could be a little bit better. Quantitative, yes. For aluminum K-alpha line input X-ray, the good database has been established. So we can frequently perform standardless quantitative analysis is possible. Accuracy, depending on what the situation is, but 30%. I don't recall who said 30%, but somebody said so. Depth profiling, yes. So our Supra has a spatter gun, and this spatter gun, argon spatter gun, can be used as in the monoatomic mode or the cluster mode for more gentle removable of, and the cluster mode would be useful for polymer depth profiling or organic material depth profiling. Analyze insulator, yes, it has charge neutralizer, but I will talk about we have to be careful with analyzing insulator or poor conductors with XPS. And green, yes, for chemical state information. XPS is very good at giving us information about binding state, chemical environment. Okay. At the end, EDS or EDX, electrons in, out is X-ray. It works okay for 6 is carbon and higher, but for quantitative analysis, we typically is believed to be sodium and above. So the spot size, or no, not the spot size, but the interaction volume in the XY dimension, it's about 1 micrometer, and the same for depth. So micron-ish, depending on the imaging parameters we choose. 1 micron, deep. Yes, it's deep. So this is why is EDS is not considered to be surface sensitive technique, but depending on whom you are talking to is surface enough. And quantitative, yes, it has typically the vendor provide a good database, so we can perform standard with the quantitative analysis. Depth profiling, no, because EDS is typically mounted on SEM chamber, and the SEM chambers do not have argon spatter gun for more, 99% of the time is possible, but typically no. Analyzing insulator, yes, we can coat insulator surface with a thin conductive layer. we cannot quote LEIS or XPS OJ samples because it kills signal from the surface a few nanometers. But EDS sampling depth, we do collect signals from a micron below, so it's okay to have a conductive layer on that. Chemical state information, no. So these are the things comparison. Okay. So this is the most important slide of today's webinar. This contains a lot of information. Okay, so we have two major surface analysis tools, XPS and LEIS, and they are connected. So we can move the samples from XPS to LEIS and vice versa without exposing to air. That's important. XPS, what we have is Kratos Analyticals, Axis Supra XPS, and UPS. And it's equipped with automated dual anode, aluminum and silver X-ray monochromatic source. Aluminum K alpha is well established and we use it most of the time. Energy of this X-ray is 1486.6 eV, while silver anode, we use L alphas, and it is about 3 keV. So for heavier elements, and for some reason, if you want to see the core binding states, you have to use silver anode. But for lighter elements or everyday quantitative analysis, we do use aluminum. So I don't believe the silver with a silver anode L alpha line, we do not have established database for sensitivity factors yet. For aluminum, yes, that's what we use it for standard less quantitative analysis. This instrument also has a capability of UPS, ultraviolet photoelectron spectroscopy. So instead of X-ray photons, you can use the UV photons from the UPS lamp helium. So it's about 20 eV and 40 eV. And as I already mentioned, multi-beam 6 multi-mode gas cluster ion source. Of course, this can be used as a monoatomic argon spatter source as well.
Are these X-ray sources considered monochromatic? Does the
it has
surrounding
monochromator.
X-ray- Right. Oh, it does has a monochromator. Right.
So it's so it's cut off. So for XPS, yes, magnesium source without monochromation sometimes used, but we don't have that capability. It's our source is always monochromated.
Right.
But everything is inside the vacuum chamber, so we don't have to worry about X-ray exposure for this tool. Okay.
Yep.
The same for SEM EDS. It's unlike your X-ray microscope or diffraction system.
Yep.
Okay, low energy ion scattering spectroscopy. Quantitative top atomic layer characterization is possible. Input noble gas are helium, neon, argon. And when necessary, we can use time-on flight mass filter. It has electron impact gas ion source, atomic hydrogen and oxygen cleaning, and capable of moving samples from 2 Kratos XPS. And our system is equipped, our LEIS system is equipped with a few more sample preparation chambers, such as electrochemical cells, the tube furnace, and some additional sample preparation units. And also in situ UHB heating is possible with this system. Okay, so let's start with LEIS. And since we are going to have a next webinar dedicated to this topic, so I'm just gonna do very basic what the heck it is. Okay, what's LEIS? Low energy ion scattering spectroscopy, sometimes referred to ISS. This is the surface sensitive analytical technique. By the way, our Kratos XPS has an option of ISS with helium ion, but we have a better resolution low energy ion scattering spectroscopy system sitting next to XPS tool. I do not think no one would use ISS option for our XPS, our Kratos Supra unit. Yeah. LEIS is closely related to both medium energy ion scattering is about 100 keV MEIS or high energy ion scattering. It's more often referred as Rutherford backscattering, RBS. Okay. The only difference is the primary ion energy is very different. While LEIS is surface monolayer sensitive technique, RBS, Rutherford backscatter spectroscopy, is used to measure samples' bulk composition and structure. And typically it's used alpha particles and 1 to 3 mega electron volts range. Okay, it's very different from LEIS. So ISS or LEIS, what's the difference? In the past, ISS was developed as an optional capability for XPS. So it shares the same the analyzer, and it's not dedicated to the ion energy analyzer. Okay, so yes, ISS has been around for some time, but not as high resolution as the modern LEIS system is. Okay. So sample damage and many things, resolution is not that great. So therefore, the current LEIS people hate being called as ISS. It's different instrument design, even though it's based on the same physical principle. So the unique thing about our LEIS system is the newly designed energy analyzer. It has this shape here, the parallel energy detection, and it has toroidal shape. And sometimes it's a modern LEIS instrument is called as high resolution LEIS. So we have to make sure it's not ISS, the old ISS. It has much better resolution than ISS era. Okay, basics of LEIS. The sample target is bombarded with the noble gas ions, helium plus, neon plus, argon plus, with energies E0 between 0.5 and 10 keV. Yeah, it's much lower than RBS. The incident ion beam is directed towards the surface at the angle with respect to the surface normal, typically smaller than 60 degrees. Our QTAC incident is normal. Incident beam is normal to the surface. It's 0 degree. Only projectiles that are backscattered into the certain solid angle are analyzed. Okay, so it's about 140 degrees from this, the incident, but it's about, yeah, so 50 from the surface normal. Okay. So due to the energy range typically used higher than 500 eV, we can ignore lattice vibrations and binding, ignore those small things. A few EV things can be ignored. And interaction with the incident ion beam and the surface atom is likely treated as a classical two-body elastic collision problem. So measuring the energy of ions scattered to this type of interaction can be used to determine elemental composition of the surface. Two-body collision model. Okay. So something is coming in with a certain primary energy. So for helium, it's 3 keV, that's the standard one, and collide with the surface atom. Then primary ion will be backscattered. That's the one we are detecting. This energy, the final state energy, EF, is K, some factor times primary energy. K should be smaller than 1. Okay. Ions, primary ions, can go deeper in the sample surface. And eventually, this kind of ions can leave the surface as well. But the energy of this E1 should be smaller than K times E naught. The energy should be smaller than the two-body collision type thing. So the interaction can happen deeper, but the energy should be different from the ions, noble ions interacted with the monolayer outside surface. Okay, so you can ignore many things. Look at the equation, E final. It's only depends on what is M1 here. M1 is the primary ion. M2, mass 2 is the target atom of mass at M2 at rest. Okay. The final energy after the elastic collision will depend only on theta, the angle of scattering, as well as the ratio between the primary ion and surface atom. Okay.
Is this why you can't determine something like an oxidation state in LEIS because it's just the atom?
Yes.
And not surrounding atoms?
Yes. So we are not detecting electron energies, right? We are still detecting that same noble gas ions, but the energy would be different after the collision.
Right, with that single atom.
With a single atom, yep. Mm-hmm. So no way for us to get chemistry information from this technique. By looking at this equation, no way, right? So let me think. However, it's sensitive to isotopes on the surface, which is not a good thing because the binary collision peak can get broader because of the isotopes can exist from the same elements on the surface. So yes, we can detect maybe isotopes, but it's not a very good thing. Okay. Okay. When we are using helium, we cannot detect hydrogen. No way, because its backscattering is not possible. In practice, we want to have more mass ratio difference between the primary ion and the target atom. In that sense, smallest noble gas ion we can use is helium, and carbon can be detected, but lithium, in theory, yes, but the scattering phenomena is not very favorable for lighter elements. Okay, carbon, yes, oxygen, yes, nitrogen, yes, in theory, but not that's easy to detect. And the other thing is when we are using helium probe ions, I mean the helium as a primary ions, like mass separation, energy separation between like iron and nickel, they are too close, okay, with the helium as a primary ion. So when depending on which elements you want to separate, we have to switch the incident ion type from helium to neon, sometimes if necessary, switch to argon. Okay, typical LEIS spectrum, it looks like this on the left side, okay? The most important features in the spectrum is the binary collision peak. If you see the peak in a LEIS spectrum, that means this particular atom, for this time it's aluminum, should exist on the outermost surface layer, period. And in addition, it has some other things happening, but I'm not gonna talk too much about here. The message you should remember is if you see the binary collision peak, any peak in the LEIS spectrum, that means that particular element should exist in the outermost surface, period. Okay.
And that spectra is collected over like an area of, you said 10 microns or so?
Typically, for the regular measurement, it's like a millimeter range, 1.5 millimeter by 1.5 millimeter
Right.
area. Okay. Because we don't want to damage the surface. We don't want to remove the surface atoms.
Mm.
So the vendor prefers to scan over large area. And
Right.
this binary collision probability is not super high. So we have to have a lot of surface atoms and a lot of things, a lot of atoms to see this one. Okay.
Got it.
So it's very different. The smallest spot size possible is 10 micrometers, but in practice, we use millimeter by millimeter area to get the spectrum. Okay, it's same for XPS. Okay, I have some TiO2 reference materials from Sigma Aldrich. And the first two was, I don't care about the phase, rutile powder, but trace metal 100 ppm. Trace metal is less than 1000 ppm. And the other one is in a different phase, anatase powder, 99.8% trace metal should be lower than 2500 ppm. This is the LEIS spectrum. Okay. So the anatase one is 99.8% TiO2 guaranteed, and the impurity should be, the trace metal should be less than 2500 ppm. And I prepared those powder reference samples and performed atomic oxygen cleaning to remove surface hydrocarbon contamination. After like 10-20 minutes of atomic oxygen cleaning, I collected those spectra. Okay. That's 99.8% TiO2 sample. The blue one is covered by potassium. And little bit of titanium peak. Oxygen is there, so I assume it's potassium oxide, covered with a potassium oxide. Both sodium and potassium, they have very high surface energy, so they tend to migrate to the surface layer. So no surprise to see something like this. Okay, it's supposed to be TiO2, but it's mostly, outer monolayer is mostly potassium oxide, this one. And the lower one, rutile, yes, I have a small potassium peak and reasonably large oxygen peak, but no titanium peak. And scattering, strong scattering in the lower energy region implies it has a junky hydrocarbon surface coverage of some kind. Okay, so this is the LEIS spectrum for TiO2 anatase phase, 99.8%. And I put this same sample with the atomic oxygen cleaning, so I transferred from LEIS to XPS. And this is the XPS spectrum of the same reference sample. When we see this one, yeah, we have a TiO2 with a small contamination of carbon and small contamination of potassium. But I can go back. It's completely different world from LEIS spectrum versus XPS. Yep. So remember, XPS sampling depth is at least a few nanometers. Maybe it's slightly deeper for the different situation. But when you see the XPS spectrum, okay, contamination of potassium as a minor element, it looks like, but in reality, this powder surface is really covered by potassium oxide, I think. So those are differences. And I try to cover more about LEIS next week. XPS. I'm spending too much time. I'm not sure if I can get to EDS, but that's okay. Okay, quantitative analysis by XPS. You can ignore all the informations, but I want to mention the most important assumption for XPS quantitative analysis. For locally homogeneous sample, quantitative XPS analysis can be performed. So you can get quantitative analysis using this XPS data, but it's not homogeneous structure, right? The top surface is coated with potassium oxide, potassium, whatever that is. And TiO2 is underneath. So you have to be careful when you want to perform quantitative analysis from the XPS spectrum, which is same dimension is different, but it's true for EDS quantitative analysis. Yeah. XPS, of course, depends on photoelectric effect discovered by Einstein in 1905. He predicted photoelectrons would be produced from the material when the energy of incoming photons exceed the binding energy of electrons in the material. The simple governing equation for the photoelectric effect is EK, the kinetic energy of the electron, photoelectron, equals to the energy of the incident photons minus binding energy of That's core electron. But this is only applicable for gas phase measurement, where electron energy is naturally referred to the vacuum level, correct, and energy of the free electron. So it's many assumptions there. In practice, for solid samples, solid surfaces, of course, situation is more complicated. Okay. So photoelectrons escaping from the sample surface has to overcome the potential barrier at the surface. That is work function. Okay, so which correspond to the energy difference between the Fermi level, FL, and the vacuum level. So the photoelectron kinetic energy of the sample equals to the incident X-ray photon energy minus binding energy of the core electron relative to the Fermi level minus the work function of the sample. So this is what the true relationship. Okay. And so many people ask me about how to insulate in samples. Why do we have to use the internal reference peak, blah, blah, blah. So I try to explain. Well, at least I need to understand what's going on in the XPS instrumentation so that I can explain to other people. Okay. Starting equation is same as the one in the previous screen. Kinetic energy of the sample equals to that. Okay. For that, if your sample is conductors and it is mounted in the conductive fashion, so the common Fermi level between your sample and the spectrometer should be established across the interface. Okay. Since if your sample is conductor, charges can be transferred from a sample to spectrometer or vice versa. So the Fermi level here is aligned for your sample surface as well as the spectrometer. Under this situation, there is a small EBC contact potential difference. Okay. Because the work function for the sample and work function for the spectrometer would be different. So the electrons leaving the sample and going into the spectrometer needs to overcome or vice versa. Okay, when its electrons is going into the entrance slit of the energy analyzer. Okay. So, but that's okay. From here, we know that kinetic energy of the sample plus work function of the sample, the sum of those two items should be same as kinetic energy from spectrometer can see plus spectrometer's work function. The sum should be the same. Therefore, we can get the binding energy relative to the Fermi level of the sample can be obtained from the X-ray incident energy minus the kinetic energy that spectrometer can see, kinetic energy of the electron that spectrometer can see, minus work function of the spectrometer. Okay. The same equation at the top. Okay. So if we can use this relationship, the binding energy of the core electron is independent of the sample work function. And spectrometer work function is an experimental constant. Okay. So
Do you have troubles with the spectrometer work function drifting? Does it get contaminated or anything like that?
Shouldn't. So once it's established, we can use it for the same value. But I think it's doing the maintenance, the annual preventive maintenance period, they may check. So
Is that calibration done during every run?
no, it's like annually,
Oh, okay.
whenever they come in for the annual checkup.
Mhm.
So once it's established, we don't see this spectrometer work function value. It's hidden somewhere in the system.
Yeah.
That's not our job to calibrate this value.
Mhm.
Yeah. So this is we can treat this as a constant parameter. And we know that incident X-ray photon energy, and this is kinetic energy of the electron that spectrometer can see. That's the measurement thing. Therefore, we can get the core electron binding energy relative to the Fermi level. That's what we are using. Okay. Okay. Therefore, photoelectrons coming from the core level always appear at the same kinetic energy, independent of the sample work function. That's the big assumption. Okay. And the important thing is that, yes, we have to hope the sample work function does not affect the position of the core level XPS peaks. The difference is always the Fermi level. Okay. This situation is under the assumption that sample and the spectrometer are in the good electrical contact. Okay. So the Fermi levels for both sample surface and spectrometer are aligned. Yeah. Then what? For conductors or insulators. And nowadays, we use XPS for polymers and oxides or whatever. So instead of Fermi level alignment, if we put the sample for conductor insulator samples in the spectrometer, what's going to happen is shared in the common vacuum level. Fermi level alignment is unlikely happening there. Okay. So the binding energy wise, true binding energy may be different from the binding energy spectrometer can see would be different. We have an issue here. Okay. So this situation is not great. So we have to do something. So let's go to the next one. Okay, this situation is called charging in XPS. I don't like charging in the SEM imaging, but after learning about how XPS energy measurement works, I hate charging in XPS instrumentation. It's a severe issue here. Okay. In the SEM imaging, yes, charging is annoying, but we are not measuring the energy of secondary electrons. So it's annoying, but it's okay. And we can put coating if necessary. It doesn't work for XPS or any surface analysis instrumentation. And charging state of the sample is unknown basically. So we have to do something. Okay. So usually in the XPS thing, so it's X-rays coming in, knocks out core electrons. So the surface starts charging positively. So we can use electron flat guns of some kind to neutralize the surface. So this is our charge neutralizers design. You can think, okay. What it does XPS with a charge neutralizer on is providing enough charge, negative charge, and hoping the best so that Fermi level aligns to the sample Fermi level should align to spectrometer Fermi level. Hoping this happens, then we can use the same equation for that one. Okay. The charge neutralizer can provide enough negative charge to compensate enough so that the both spectrometer and the sample surface can share the same energy, Fermi level. If it doesn't happen, we are in the big trouble, but it's natural. Sometimes it's not perfect because we do not know what's happening in the energy levels there. So what we are hoping is providing enough charge neutralizer, basically the electrons, and eventually it's get to the good Fermi level aligning between them. If it's slightly off, that's okay, but we have to use the internal reference peak to be safe. Okay. That's what we are hoping. It's very tricky situation, sometimes challenging, but as long as we can find a good internal reference peak location, energy location, then we can talk about chemical environment, binding, more accurate binding energy calculations for conductor systems. Well, I don't have time for EDS, but I should talk about the OJ effect. It's important. We observe OJ peaks in XPS spectra. Okay. What is OJ? You might have heard it, but it's complicated. The multiple step process. So let me explain it to be clear. Okay, OJ first core electrons are knocked out. Okay. In the OJ electron spectroscopy, incident beam is electrons. But in XPS, X-ray photons can knock out core electrons. In the core level, we have hole, vacancy there. Okay, this is unstable energy situation. So we have to this atom needs to do something. The one way to make it more stable is you can fill this empty site, empty electron, by moving the electrons in the higher energy state coming in, then the energy difference is emitted as a photon. For most of the cases, this photon energy belongs to X-ray region, therefore, it is X-ray fluorescence. If X-ray fluorescence, XRF, incident is typically X-ray in and X-ray out. Oh, this is also EDS, okay? EDS system incident is electron beam, and we detect characteristic X-ray photon to determine which element it has. In the OJ process, can happen, okay. It's same for the next step. The energy with a slightly higher level can fill in here, and instead of emitting photons, the an electron from different, or could be the same shell, can be emitted as an OJ electron. Okay. This is no photon emission, so radiation-less process. This is OJ. OJ peaks. So this is something. XPS spectrum. It shows carbon oneness, oxygen oneness, and also the oxygen OJ peaks. OJ process involves many things, so it has a particular shape. Yeah. Therefore, it's useful to use OJ peak location and shape for identifying some elements in XPS spectrum. Okay. The difference between OJ electrons and photoelectrons. OJ electrons are emitted with kinetic energies that's only dependent on the electronic state of the element responsible for that ejected electron. Yeah. So that means in the kinetic energy-wise, it's independent of the incident X-ray energy. Okay. Unlike the photoelectron lines, changing the X-ray characteristic energy does not alter the position of the OJ lines if we see it as a kinetic energy scale. However, in the XPS spectrum, we see this spectrum in the binding energy scale. In the binding energy scale, photoelectron locations do not change even if you change incident type of incident X-ray photons. But OJ features will move because kinetic energy stays the same. But we have to convert to that binding energy scale. Okay. So that's why when we see the XPS spectrum in the binding energy scale, OJ peak location would be different depending on which incident X-ray you use, while XPS peaks do not move in the binding energy scale. OJ parameters. Modified OJ parameter alpha. What is this? Not dash. Sorry, prime. Can be used when you wanna get accurate chemical binding state information. It's useful. Okay. I don't know how popular this method is, but there's a established procedure for using the combination of OJ peak locations and photoelectron locations, get the more accurate, at least trying to get a better state, chemical state information from there. Okay, it's
So
1
the
hour.
OJ, one last question, if that's okay. So
Yeah.
is the OJ response required for oxidation state analysis?
No. Many people do use like a carbon 284 EB difference peak, and if you know the chemistry well, you can use just the internal reference state. But for the more complicated system like transition metals or something, it's if you want to know if this is the nickel oxide versus carbonate or something, then it may be useful to use the photoelectron energy together with the OJ parameters, because any offset, okay, here, the modified OJ parameter is independent of X-ray energy used. And since any surface charging shift would be the same for both peaks, but the opposite direction. So that shift would be canceled out. So we can use this, that difference between the binding energy and, no, not the difference. Sum of the kinetic energy of certain OJ peak plus the binding energy of the location, then this one, you can compare this value for some oxide versus metal or something. That's,
Right.
I believe, how it is used. For carbon, with aluminum, carbon OJ peaks does not appear with aluminum K alpha signal, K alpha incident. It is slightly above 1200, so we cannot use this method for carbon chemical binding information, but oxygen, yes. And some other element, possible. Okay, so what should I do? Is it a good time to stop? But to be continued, but remember this figure, EDS, we are measuring this X-ray. Okay. Of course, during the surface of our XPS measurement, X-rays are emitted. Characteristic X-rays should be also emitted as well, but electron energy analyzer cannot see photon emission. No way to analyze photon energy. Therefore, it's completely ignored in the XPS spectrum. One thing I wanna say. Standardless quantitative EDS analysis is possible, but you have to be careful, okay? We are assuming in the same as XPS quantitative analysis, but for EDS quantitative analysis, we are assuming we have a uniform, locally homogeneous structure over 1 micrometer or a few micrometers sampling volume, okay? So if you have a layered structure there, standard method for quantitative analysis does not work, period. It's same for XPS quantitative analysis. So you have to be careful with that thing. What else do I have to say for XPS? Sorry, the EDS. Well, I should stop here. Not only that, with the EDS, yes, you can do the, but topographic samples, EDS signal is very sensitive to the local geometry, so you have to be careful. So for the standard good quality quantitative analysis, we wanna polish the surface. Sorry, we can polish the sample, okay, so that we can get more reliable spectrum without any topographic issues here.